Hello everyone, welcome back to CSC Core Concepts. I am Dr. Sonali, and in my earlier video in the series we have talked about overview of the CNN model and as if what are the steps of the CNN model. So in this video we are going to start with the convolution and the ReLU activation function. That is the first step what is performed during a CNN operation. So basically that is a convolution operation, and as I have spoken earlier that for a CNN model the input is our image. So our image is basically a two-dimensional image. Okay, so let us talk about an image which is in the form of a matrix. Okay, and this is our image, and what we are going to do is that we are going to extract the features of our image. The first step is to extract the features. I had given the example of an apple and a banana, so we have to figure it out. We have to find out which are the features, which will help us in identifying which one is an apple, which one is a banana. Now, if you go to my machine learning series, there we have discussed this point in detail, that what is the difference between ML and NN. Okay, so those features are fed into the system in case of ML, while in neural network, this operation is done by the system model itself, right? So let us see how does it performs this feature extraction operation. So let's get started. So basically it is going to use something called as a kernel or a filter. So filter is going to slide over the image one by one, and as a result of it, it is going to create some input results, and these results are called as the feature maps. So you cannot have only one feature map, right? So if you have a fruit, let's say apple, orange, banana, so they differ in their size, the shapes, the color. Okay, so each one of them are each features. So one feature map is not enough, so here you require multiple feature maps and to figure out the difference between them. And I spoke about something called as a kernel or a filter. So what is a kernel or a filter? Basically it has to be smaller than the input data. The size of the filter should be smaller. Let's say for example your kernel size is your image size is, let's say, 100 cross 100. Okay, so your filter size can be, let's say, 3 cross 3 or 5 cross 5. Okay, so it is again, a filter is nothing but a two-dimensional matrix, and then we perform a multiplication between the input image and the filter. So the three elements which enter into the convolution operation are, first of all, you are given the input image which is going to enter. So this is your input image, plus you will have a filter which is smaller in size, and you get something called as a feature map. So we are going to perform the multiplication of these two, that is the image with the kernel. So how to, let us define the kernel. Let us break this into further processes steps. So you have to define the kernel. So the values within the kernel determine which feature it is going to detect. Let's say sometimes you want to have the features of the horizontal edges, vertical edges, the sharpening filter, the sharpening borders or the edges, blurred borders, whichever. Okay, so in case of some shapes you require the border edges, right? So how much sharpened they are. So you are going to define the kernel in that way. Second is the sliding window process. So sliding window means what? Basically you start the kernel by placing it on the top left side on the image, and slowly one after each operation you are going to slide it one by multiplying and creating a summation. And based on that the output is nothing but a feature map, that is again a new matrix, or a, you can say, a smaller matrix than the original image, and it is going to represent some of the feature. And this step is going to get repeated until you complete the whole input image is covered. Let us have an example to see this. Okay, so basically with the example you will understand more. So you consider that this is your input image, right? So this is our image, and you can see the image is formed of zeros and ones. So wherever there are ones, you can say these are the areas which are highlighted areas, and rest is zero. So this is an image, and I want to extract the features of this image by using one kernel. So let us say kernels are also called as the feature detectors, right? So I have discussed, I have created this kernel. Let's say for example, okay, so what is the size of my input image? It is uh, for 7 cross 7. Okay, so the my input image size is 7 cross 7. Okay, and what is the size of my feature detector? It is 3 cross 3. And I told you that feature detector always have to be a smaller smaller size than the input image, right? Now if I multiply one at a time, and I will get a feature map, and the feature map will be of size what? Feature map will be of size 5 cross 5. Now how do we do that? So let's see, again another feature map. So this feature map and this feature map, it is going to, this is the final one, right? So let us see, you can see a highlighted area over here. Let me just show you in detail. So you can see one highlighted area, this dark black circle. So you are going to place this kernel on the top of this image. So when you are going to place this kernel on the top of the image, you can see this is a 3 cross 3, so it will only cover 3 cross 3 portion. See, if your feature map is a 5 cross 5, it will cover the 5 cross 5. So you are going to perform some multiplication operation. So 0 is multiplied by the first row first column is multiplied with the first row first column of the feature detector, and so on. And the in or the output of this first row first column, you get it 0 after multiplying. So similarly here you can see after performing the whole multiplication, this is the result you get. And this feature map, this is a feature map which is indicating some of the features. So this feature map is reduced in size as compared to the input image. See, basically what happens is that whenever you have an image, no, all the areas of the image or all the pixels of the image are not contributing. Let's say for example, if this is your image and there is some fruit, okay, the rest of the background is what? White or green color. So this background is not contributing anything, right? So easily you can discard those areas which are not contributing. So this is, let's say, a shape. So you want to figure out this object, right? And rest of the background you want to remove it. So you can have a feature map which can extract the features of the edges of the triangle, the colors of the triangle, and so on. Okay. So let us see one more example. Let's say this is our input image, and you can see this is a colored image. So the values are there, some values are there, let's say 9, 4, 1, and this is how the image looks. And this is, let's say, our filter. So this image is of size 5 cross 5, and the filter is of size 3 cross 3, right? So now when you are performing this multiplication over here, I'm sorry, yeah, so when you are performing the multiplication, you can see how the multiplication is been done. So the first you have to find out the zeroth value, right? Zeroth row, zeroth column. So how are you computing here? 9 into 0, that is the first entry here. So you can see over here, yeah, so you can see this is 9, this is 9 multiplied by the first value. Okay, so first row first column multiplication plus 4 multiplied by 2, so this is 4, it is multiplied by 2, and so on, it is done, right? And basically this is done, and you get the answer somewhat 16. So each of them are multiplied one by one. So uh, uh, now, okay, so now when first step is done, what will you do? You are going to move your filter one point at a time, right? So let's say here again you are moving the filter on this patch. Okay, next. Now how much you are going to move, right? This is first. Now you are going to move to the second column, or you are going to directly move to the third column. That depends on a feature which we called as stride. Okay, so you can take, if you are taking the value of stride as 1, then it is going to move one column at a time. If you are taking the value of stride as 2, then it will move two columns. Understood? So this is how it will work. So let us see some interesting example. So let us consider this image. This is a 5 cross 5 image, and for that I have considered a 3 cross 3 kernel. So goal is, let's say this kernel I have designed to detect the edges. Okay, so I want to detect some of the edges of my image. So based on the detection, what I want to detect, I have taken the kernel values. Okay, so the kernel is designed in such a way that it will highlight the center pixel much. You can see the center value is 8. Okay, so the kernel is designed in such a way that the center pixel will be highlighted than its neighbors. This type of feature means sharp changes. So basically what I want here, I want to find out the sharp changes or the edges, detect edges in my image, right? So if I want to detect the edges in the image, I have taken a higher value in the center, and rest of the neighbors are having the same value. So now let us say, for example, this is my image, right? So I will start my 3 cross 3 kernel by placing it like this. Okay, I am going to place it on my image in this form, and I am going to perform a multiplication. So 50 will be multiplied by -1, then again next 50 will be multiplied by -1, and so on. So initially you can see 50 is multiplied first column of the kernel multiplied by the first row first column of the filter. So first row second. This way you perform the multiplication, and what is the answer you are getting? That is 150. Okay, so now this 150 is the first value on the feature map. You can see this is the feature map. This 150 is the first output. Now you want to have the second output. Okay, very good. So 150 is the first result, done. Now if you go to, now what you have to do, you have to slide, means you have to move to the next position, means move the filter after one position. See, so because we have taken a stride value of 1, it will move only one position, right? Now this image will be, now this 50 will be multiplied by the first value, and so on. So one by one multiplication will go on. So it has slided to the next column. So when you have set your patch to the next column, the next value suppose is coming 200, right? Similarly, you go on repeating until you cover all the pixels of the image. Understood? So finally, you can place the values what you got, 50, 150, 200, 150. So you can see here the center value is very high, that is 600. Okay, other pixels are in the range of 150 or 200. So if, because it was there in the kernel, you had a center value very high, that is 8. So it is effectively highlighting the distinct central area. Supposedly you don't have this value coming so high, okay, and you are, even after keeping the kernel value 8 at this position, still if you are getting a very low value here, that will reflect that the original intensity was very less here. It was smooth area, it is not an edge area. Now because of its original intensity was very high, already high, and you multiplied it with a higher value, you are getting a distinct value. If you compare other values, they are almost similar, right? So they are the smooth areas of the image, and this is standing out, that is 600. The change is very high, so it is reflecting the edge area. Okay, so this way, this is the first feature map you have created. So we can create multiple feature maps, okay, because one feature map is not enough to identify each objects, right? So each distinct filter will give you, so this filter was to detect the edges, another filter you may use to detect the dark colors. Okay, so this way you can have multiple filters, and all filters need to be of same size. It is not important. So a single convolution is designed to use a specific number of filters. So how many filters generally we use 32 filters, means 32 feature maps, 64 filters, then you can have 128 filters. Okay, they are, the more filters you use, the often increasing in the deepen layers. So inside layers you use more number of filters. Then this filter performs its own convolution operation, and it will give you the feature maps from the previous layer, and one feature map. So first filter ka feature map will stack on the second one. Then it will stack on the third one. So it will look something like this, stacking of the results. You can see the first, second, third, fourth. Okay. So one, two, the first filter, second feature map, third feature map, and this way one after the other they are stacking. Understood? So this is since each filter starts with a different random initial weight. Okay, and learn during the training, they specialize in detecting different patterns. So itself it is learning. The first time it may fail with the weights, right? It may not go correct. So next time it can change its weight and find out other features. So one filter might become a vertical edge detector. One filter might be finding out all the vertical edges. Another filter might be finding out the horizontal edges. Some filters might be finding out the texture of the image. So in deep layers, filters combine all these features to detect very complex shapes, colors, or object part. Let's say you want to detect a circle from several curves, or an eye. Okay, suppose you are given the face of a person, right? So if you are given the face of a person, there are so many features. There are eyes, ears, nose, so many things are there. But you want only to see the find out the eyes. So these features, so these have many features: the color of the eye, the depth of the eye, the edges of the eye. So by this you can have this complex problems solved, like you have face recognition and all. Okay, these softwares work. And then each of the filter is stacked. So features are also 2D maps. So all these individual features are stacked onto one another, and they allow the network to reach a very rich model. Okay, which can map diverse features. So this is how your feature map will look like. And a complement and the step, another step with this convolution is a ReLU. So basically what does a ReLU function does is that it is very crucial. It is going to perform the non-linear activation. Non-linear means it introduces non-linearity into the model. See, so element wise thresholding function, we have studied about ReLU activation in machine learning tutorials. Please go through the activation function where we have discussed this formula. What does ReLU does is that any negative value is mapped to 0, otherwise the original value is kept. Okay, so if the value is already positive in the feature map, it will remain unchanged. If it is 0, if it is negative, it will become 0, because the image contains many non-linear features. Non-linear feature means transitions, edges, color change, so many things. So if you don't have non-linearity, then same input and output will be same for a linear function, right? So non-linear is going to highlight. Let's say for example, if you have using a linear classifier, okay, and you are using classifying a 2D data point belonging to two class. So let's say for example, here you have you have some data points, right? And you want to use a linear classifier, you can easily classify. But if the data is not linearly separable, okay, you can remember the XOR operation. So in that case, linear function cannot separate. Okay, linear function is not able to separate the two types of data. So you have to use a non-linearly separable classifier, because they can create a curve or a 3D boundary to classify the patterns. So here it is not something like that you can only use the ReLU function. You can use other activation function also to introduce the non-linearity in the image, but the which function to use depends on the problem and the type of data we are working. So, but ReLU is why it is a used choice, because it is very very fast and it speeds the training time rather than other functions such as a tanh or an sigmoid function. So I suggest you to go through the activation functions in detail so that you can be very very clear why do we require the non-linearity in the image. So non-linearity, suppose this is your feature map, okay, what you got. So here you can see there are some negative values. So these negative values will be converted to 0 when you perform the ReLU activation, and rest of the values are same. Okay, so you can use a non-linear activation function, because in case it is not linearly separable, let's say these are the data. Okay, so you can see some mixed data, it is not linearly separable data, so you can use a non-linear function which can take the shape of a curve or something to separate. Okay, so that is all about the first step on the convolution function. I suggest you to please go through the activation function and ANN tutorials to be very much clear about the separable data, non-separable data, and the activation functions, and the nature of the activation function. And in the next part we are going to discuss about the other steps of the convolution of the CNN model, that is our pooling and dropout flattening. So please don't forget to like, share and subscribe to the channel, and keep an eye on the channel for more such informative videos. Thank you.